my name is Jenny Hamilton. I am a big fan of ISS. Most of my career at NASA has been related to the International Space Station. And so it is just always a thrill to get to talk about and share the story of what the ISS is doing, especially as it comes to how it benefits life on Earth. So we'll be starting with a little bit of history, some quick facts about the International Space Station if you're not as familiar with it, and then go into the areas of research, kind of a couple of different examples as well in those different areas, looking towards the moon and Mars and those longer exploration missions, as well as benefits to life on Earth. And then, yeah, like Stacey said, we'll have Q&A at the end. Since I'm sharing my screen, I can't quite see all the Q&A things like in the WebEx at the moment, so Stacey will keep me honest if there are some questions in the middle. So with that, we'll start with a little bit of history. So for the station, it was launched in 1998. It is involving the US, Russia, Canada, Japan, and then the participating countries of the European Space Agency. So it's pretty suffice to say the ISS is one of the most complex international collaborations ever attempted. So the ISS has been continuously occupied since November of 2000. Next year, November 2nd of 2025, will mark 25 years of continuous human presence in space. And Expedition 1, that first long-duration stay, was started in November 2nd of 2000. So if you have any family members, anyone who was born after that, they have never known a time where someone wasn't in space, or we like to say also, they've never lived where the entire human race was on Earth. So the first module, like we mentioned, was Zarya, and so it was flown in November 20th, 1998. Zarya means sunrise, so that was the first module that flew up. And then the large modules and other pieces of the station were delivered on 42 assembly flights. 37 of those were on the US space shuttles, and 5 were on the Russian Proton and Soyuz rockets. And then we say assembly complete in March of 2011. But there have been some move arounds of the modules and also some other test modules that have flown. And so it's kind of still a little expanding, but most of the major part of assembly was completed in March of 2011. So some quick facts for some perspective. This is the size of the space station over an American football field. A soccer pitch has, I think, a similar length, but it's a little bit wider. So it is traveling at a speed of about 17,500 miles per hour, faster than some of our highways. And in 24 hours, the space station makes 16 orbits around Earth. So every 90 minutes, the crew goes all the way around Earth, and every 45 minutes, they see either a sunrise or sunset, which can throw off your kind of sense of light and time. So the pressurized volume, the living space, you can kind of see the middle portion with the kind of T shape in the middle is the livable stack. And we say this is approximately about the size of a 6-bedroom house. The solar array wingspan is longer than the world's largest passenger aircraft, the Airbus A380. And so our wingspan is about 356 feet in comparison to the 262 feet for the A380. Its orbit at that 250 miles above Earth, so in low Earth orbit or LEO, you might hear me say either one. This orbit it goes around causes it to pass over more than 90% of the world's populated living area, which makes it a great platform for observing our Earth and kind of looking back down at our planet. And we'll talk more about that later. And then 8 spaceships can be connected to the space station at once. And of course, international is built into the name, so we wouldn't be where we are without our international partners. So we do have an international crew of about 7 people who live and work while traveling at that speed of 5 miles per second. Sometimes we have a few more on station during a crew handover. So when one crew has flown up and we're still waiting for a crew to return to Earth, there might be a couple more folks on board. Over 270 people from more than 20 countries have visited or lived on the space station. And then we have those 5 international space agencies that are the managing partners, and that represents about 15 countries operating and managing the International Space Station. So those are some quick facts, but I know we're here to talk about research. You're like, Jenny, what's the point of this big hunk of metal in the sky? That's great, space is great, cool. What are you doing? So the International Space Station is a research laboratory. It was designated a U.S. national lab by Congress back in the early 2000s. And the astronauts 9 to 5, their day job is the science on board. So what is it exactly that makes research on stations so unique? So it provides researchers and scientists access to these, we kind of categorize it into these three unique features of low Earth orbit, or LEO. That long duration microgravity, sustained microgravity, that lack of Earth's gravity, the exposure to space and that extreme environment, and then that one-of-a-kind view of our planet that lets them conduct these really innovative experiments. So for sustained microgravity, that one in particular is a game changer for scientists across a lot of different disciplines. For example, removing gravity gives biologists this unique insight into the stress responses of the human body or plants or other living organisms. And a lot of the things that, we have to think of different ways to drink water or eat our food, a lot of different physical and chemical processes as well that we'd be used to on Earth completely change when you remove gravity. And the information we get from studying that can help with studying phenomena back on Earth and improving things on Earth as well. So the orbiting lab's location at the upper edge of the Earth's atmosphere also allows researchers to expose materials, electronics, even microorganisms, things like that, to that harsh space environment for long periods of time, and then return those items and samples to the ground for detailed analysis. And that's not only to improve spacecraft and future exploration materials, but can also help to inform materials used on Earth, any kind of structural kind of thing that is, we can look at how to improve durability, or improve degradation, anything like that, and those applications can come back to Earth. And we'll dive more into this, but talking about observing Earth, using the space station, we can look at different atmospheric phenomena from a totally different viewpoint, even looking at natural disasters. So having a human crew on board provides options for us to look back on Earth that is not available with typical satellites. So they can collect unscheduled data from unfolding events like hurricanes and storms and volcanic events and eruptions, which they have done before, with digital cameras on board with their unique viewpoint, and kind of report back to us. So that's about the research, about how much research has been done on station. So we have, over the lifetime of station, we've had more than 4,000 experiments representing over 5,000 researchers from over 100 countries. So now more than ever, we've gotten a lot of discoveries and developments that are taking shape. We've also had publications in over 4,000 journals. So you see like Nature or a couple of these other larger publications. And so we're really in what we call this decade of results. So the first decade of ISS, we kind of see as this decade of construction, of building. The second decade was growth and, finding these lessons learned from how to operate in space, what we need to do, how do we do science. And now we're really hitting our stride with getting results, not only from the science that was done over the past 2 decades, but also expanding exponentially in the kind of science we can do, the kind of results we're getting, and bringing that back down to Earth, and also to help prepare us for those future missions. So that is a little bit about space station in general. So now we'll talk about some of those specific science fields. So one of our fan favorites, of course, is plants in space. We love talking about how things grow in space. So as NASA plans those long duration missions to the moon and Mars, a key challenge we have is figuring out how we're going to feed crews. How are we going to keep them supplied with food over the weeks, months, and even years in space? So researchers are looking at growing plants on board space station to prepare us for those missions beyond LEO and low Earth orbit. We've tested several types of plant habitats. Obviously, as things are floating around in microgravity, we can't really, go to our Home Depot or Lowe's and buy a bag of dirt and fly it up, right? It would get everywhere, first of all, and isn't as conducive to growing plants. So we're looking at different ways we can either contain that dirt, kind of have that traditional growth, the growth method. We're also looking at different methods, including hydroponics, so just growing only with water, or aeroponics, just with them floating in air, and some other non-traditional ways to grow plants. It's not only for food. This kind of greenery within remote environments can also really positively contribute to behavioral health for the well-being of our astronauts. So many crew members report, just caring for these plants, having this little bit of green in the International Space Station is some of their favorite activities. They find it really enjoyable and relaxing. And that's also a very important contribution. We have to think about the entire human system, including mental health, as we're preparing for those future long duration missions. Some of the items that we've grown on board include chili peppers, dwarf tomatoes, so many different lettuces, and a lot more. And it's not only helping us for exploration, the research on space station can also provide and improve food production on Earth. Because we see these plants in this really stressful environment, we can better understand how they adapt and develop new strategies and technologies for growing crops in reclaimed or remote habitats or different kind of environments. We had one fly up recently that's looking at how plants react to different water levels. So looking at how a plant reacts to just drought or just overwatering or a nominal amount of water, and how it adjusts to that, which can really help with those kinds of areas that experience those conditions back on Earth. So when it comes to drug development, developing new and effective drugs is a very long, expensive process, both to identify the drugs that might work and also then to test their effectiveness and their limitations, which is where space station research can help. So the space station's unique microgravity environment can allow these really delicate structures in like the microscopic level of drugs to form better. So this capability gives our researchers this platform for testing and development that's not possible on Earth. So for example, we talk a lot about protein crystals, like these tiny building blocks in drugs. And we call it PCG, if I slip and say that acronym. So in many diseases, the proteins that trigger the disease fit into very specific locations, like a biological keyhole. The protein of a potential drug for treating that disease has to be designed to fit that keyhole, and then a good key and keyhole fit results in a more effective medicine with fewer side effects. But to achieve that fit, then scientists need this really detailed knowledge on the structure of both proteins. And one of the best ways to analyze that is to look at it in crystal form. So it's a lot of technical jargon, but basically, being in microgravity without microgravity lets us find these structures that are more clear and easier to find, that way to match those proteins so that we can create these better drugs. So for more than 2 decades, actually, the International Space Station has provided this platform for growing and studying protein crystals. I think one of the very first experiments we had, even before we had Expedition 1, was with PCG, with protein crystals. And we discovered that they grew in space in a more uniform and even larger than those grown in Earth's gravity. So since then, we've had drug companies and academic researchers that have conducted hundreds of these PCG experiments. And it's by far the largest single category of experiments conducted on the orbiting lab. And that's just one way it advances drug development for patients back on Earth. One success story we love to tell from station is that this PCG research helped to reduce the timing for a cancer treatment. So there's a drug called Keytruda that was originally had to be administered through an invasive port administration into the body, and that could take up to 2 hours of sitting and receiving this medicine for the patient. Well, research done on space station reduced that time down to about 20 minutes through an IV. And the further research being done on station is actually looking now at taking it to just a quick injection, like a flu shot. So taking it from that very invasive 2-hour port administration to something you could, as quick as going down to your pharmacy and getting it, maybe not in the same sense, but in the same timing sense. And so that new flu shot version of it is actually in phase 3 clinical trials. And so we're hoping this research makes cancer treatment more convenient, improves the quality of life for those patients, and also has the potential to significantly reduce the cost, making it more accessible to more people and more patients. A couple other examples here. There on the bottom left, you can see this comparison side by side of the crystal So these were actually insulin crystals that were grown on Earth there on the left, and then in microgravity on the right. And so results showed again that the crystals were larger and they were better structured, which could really improve pharmaceuticals and those treatments on Earth. The one up in the upper right corner was a crystals formed inside the Japanese module in Kibo on space station, and it was actually a JAXA study as well that helped to improve a drug for Duchenne muscular dystrophy. And so they're looking forward to how that drug can help more effectively treat those patients and hopefully extend their life expectancy as well. So we do like to tell people we do set fire in space, but in a very controlled environment. So microgravity enables the study of physics, the physics of the universe through this completely new lens, right? So we are discovering this fundamental knowledge by doing research on these really basic things like bubbles and fluids and fire. So on Earth, when you light a candle, you can see that it has more of a tear shape, right? And that's because of the natural buoyancy of Earth, because it's being drawn down by gravity. That actually stops us from fundamentally understanding how flames work. It sounds silly when you're like, well, I see the flame, I know how it works, it's just like that. But the physics behind it, we don't always understand on Earth. And so in microgravity, that buoyancy isn't there. So instead of the teardrop shape, this one, the animation you see here is a different experiment, but if you just have a flame by itself, it'll actually burn in a sphere. So a nice little globe of flame. And so that allows scientists to better study the physics of flame spread, which we don't just do for fun. We do look at the physics of fire, and that can help to do things like improve models of how wildfires might spread. Another kind of fire that's actually discovered on space station was a cool flame. So cool flames are flames that burn at extremely low temperatures, and they're nearly impossible to create in Earth's gravity. But they're easily produced in microgravity on the ISS. And so this non-premixed cool flames were first discovered in 2012 aboard the space station, and it helped spawn this rapidly growing research field into the nature of cool flames. And this is really applicable to Earth because for internal combustion engines, temperature plays a really key role in both engine efficiency and the production of any pollutants coming from your engine. So if engines could be designed to incorporate aspects of cool flame chemistry, they would run cooler, which means they could run cleaner and also more efficiently. Now, of course, we are big space nerds, so of course we want to look out and observe our universe, and the outside of the International Space Station is the perfect place to do that. So it does provide this perch for these different experiments and instruments to look far into and beyond our galaxy, looking at information ranging from the locations of black holes to the makeup of the universe itself. So instruments using this vantage point include NASA's Neutron Star Interior Composition Explorer, get that acronym right, or NICER, which is a little more palatable. So you're like, that's great, neutron star is cool. Well, neutron stars represent this really dense matter, the densest matter that we know in the universe. Any denser and they would implode and become black holes. So we don't really know how matter behaves at these super high densities because we can't reproduce them in any experiment on Earth or in the solar system. So studying the physics of these stars provides this new insight into matter and the basic building blocks of life and everything on Earth and beyond. And actually studying these stars could also provide a future option as kind of like you could think of a GPS for future space missions. Looking also as well at studying and monitoring the cosmic rays, which are the high energy particles from those distant stars, could also help protect our crew members when they're traveling to Moon or Mars. And so I mentioned NICER before by name. This NICER observes neutron stars by looking at X-ray bands they give off to look into their structure dynamics and energy. But to do that, we had to develop a new way to use X-rays, and Massachusetts General Hospital took interest. So Mass Gen Hospital and the NICER teams worked together to use NICER technology to create modulated X-ray sources that can be mounted around a patient who might need something like an MRI, firing when needed. So this technique can decrease the amount of radiation that a patient is exposed to and also improve the image quality for that level of radiation. And as we're looking out, we are, of course, looking at how space flight affects humans. Of course, that's essential as astronauts are moving from LEO and low Earth orbit to the moon and Mars. And so we're preparing human missions to Mars with a stepping stone approach to expand our presence farther into the solar system. Under the Artemis program, the agency is kind of combining the knowledge gained on Earth plus the research gained on space station to then learn to live and work on the moon and eventually prepare for missions to the red planet. We provide insight into how the human body adapts to 5 hazards. We kind of categorize them there, and you can remember them, another acronym, with RIDGE. So radiation, isolation, distance from Earth, gravity, and then closed or hostile environments. And so we'll look at that suite of hazards, how the human body reacts to those 5, and make sure that we have a comprehensive picture to not only help our crew survive, but also thrive on those future missions. So the last couple of slides, we'll just talk about looking back at Earth. So we've talked a lot about looking out, now looking back in. We talked already about some of the unique perspective that the International Space Station provides, not only with its view of Earth, but also with its orbit. And so it does provide a wealth of data to monitor things like climate change. We can do that using 3 main platforms on the International Space Station. The other kinds of instruments that are mounted outside that look down on Earth instead of up. We also use the International Space Station as a platform for deploying satellites or CubeSats, and that can also be new observational platforms. And also just the windows that the astronauts are taking photos outside of. So we've actually had more than 4 million photographs of Earth taken over the lifetime of ISS. And those have contributed to research on our atmosphere and climate change, monitoring and the response of natural disasters, like I mentioned. And the instruments mounted on board, in addition to some of that data, has already been used to help reduce heat absorbed by city surfaces, reduce fire risk in forests, measure plant stress, track greenhouse gases, even helping farmers efficiently water their crops. In combination with our plant research, we can kind of give that information back down to Earth to help those people maintain their crops more efficiently and better. And then lastly, we've talked a little bit about the human research for life on Earth. So of course, the space station does help us understand how humans can thrive in those far-flung planetary destinations, but we can also help to address complex human health issues on Earth. So we provide this platform for long-term microgravity research to foster these breakthroughs that can yield benefits to patients back here on our planet. So many crew members, for example, they experience changes to their bodies in space that are similar to that associated with aging, so including immune suppression, stiffening of arteries, as well as bone and muscle loss. So those conditions normally develop over decades on Earth, but they are slightly accelerated in the space environment. So there's a growing body of research for that as well that takes advantage of this fact to then develop strategies that could also come back and prevent and treat patients on Earth while also protecting our future crew. We talked a little bit already about cancer research. We're doing a couple different ways that we're contributing to cancer research is by cultivating stem cells, looking at those protein crystals, and also looking at organoids, basically these mini organ tissues. So with microgravity, cells can form 3D structures more easily and readily. And so in space, we can create these tiny organ tissues that are more true to life and are also better for testing in microgravity. So they act in microgravity, they act more like they would act inside your body. So we've created and flown a variety of these kinds of tissues, from cardiac and heart tissue to brain tissue to specific tumor types. And so the ISS is this great environment for building those more true to life models and then testing the drug treatments that would be used on Earth to develop detection tools and therapies for a wide variety of precancer or cancer. We've already used this method, actually, this approach on board earlier this year. We had tumor organoids that were treated with an FDA-approved cancer drug. You can see it in the left grid, the left green and black grid. So this is a current drug that's FDA approved, but we tested it on those tumors with a new drug also built off of space station research that was able to stop tumor growth more efficiently. So it's a really great stuff coming out of that field of research. Similar things can be applied to Earth to bioprinting. So bioprinting, you can think of like 3D printing. It uses living cells, proteins, and nutrients as the raw materials, and has the potential to produce human tissues for treating injury or disease, or even creating entire organs for transplants. So the picture up there at the top shows a knee meniscus that was printed on board by red wire last year. And so this is the cartilage between your knee bones. And it is coming back. They're still studying it, but it is looking to be better quality and could eventually lead to these really high quality transplants for people who need knee replacements in the future. In addition to that, this having to think about the medical challenges of helping a crew on the International Space Station, as well as on those longer missions, has to make us more innovative technology-wise. And thinking about that remote care can also help us to help patients in remote locations on Earth that don't always have easy access to medical facilities. So a couple just quick things at the end here. We are also a platform used by small businesses and entrepreneurs and researchers to test their science and technology in space. We have over 50 companies that are already conducting research and development in space, and we're really supporting that opening up that economy and having that thriving economy in low Earth orbit by helping to develop and passing our lessons learned for future commercial platforms, commercial space stations, as well as private astronaut missions. And we're also looking, of course, towards the future. For over 2 decades, we've had this opportunity for research in a way that no other platform has been able to accomplish. And understanding how to live and work in space does help in the development of technology needed to enable our reach to expand further into our solar system and further out, helping to improve things like air and water filtration and waste filtration loops and things like that, reducing expendables that have to be resupplied or carried, and all of those things that we have to consider and be innovative for space can help to improve things back on Earth. So you can follow us more. This QR code here is a one-stop shop for links and apps related to ISS research and technology, including an app that lets you track where you can actually see the ISS fly over where you are and find that timing, as well as a big searchable database of every single experiment that's on board ISS, and lots of the news stories and great things coming out of NASA there. So thank you so much. I hope you learned something new today. And if there's anything you remember from this presentation, I hope you remember it's off the Earth, for the International Space Station. So thank you so much.